Yes, so thank you for the introduction. So, doing the talk first, let us introduce maybe some notation, because of course everyone uses a little bit different notation. That's how it is. So I write this wave inequality for isomorphic Banach spaces and just regular equality for isometric isomorphism. This is, I consider such Banach spaces equal. If I can embed one space into another, I write this this wavy arrow and double arrow if there is a continuous linear surjection. And for some topological space, recall that character of a point is the minimal cardinality of basis at the point x, and character of a space is supremum over all points in the space. It will be useful later. I will be mostly concerned with CK spaces. So many guys have talked about those spaces, so I will not introduce them. So first is a teaser, some old problem which is related to mine problem, right? So this is this problem by Banach, whether the functions on the unit interval and on the unit square, whether the spaces of functions are isomorphic to each other. And this is well known so far that, yeah, they are isomorphic because, of course, Millioutin's theorem, right? But we can generalize this problem. Because, well, unit interval is, of course, linearly ordered compact space, right? This so-called compact line. We can ask the same question, but for any compact lines, not necessarily metrizable, not necessarily the unit interval. And that's basically the question I was working on, whether we can take two products of compact lines and ask whether the functions on them are the Banach space of functions on them are isomorphic. That's just the basic setup. Okay, so what do we know? We know, of course, that by Millioutin's theorem and also Bessaga-Pełczyński's result, metrizable spaces are not very interesting, right? Because product of metrizable compact spaces is metrizable, so we have already some characterizations for it, so we know basically everything. So what happens for a non-metrizable case? So there is this theorem from 2020 by Michalak, which is very nice results for separable compact lines, that if we have different amount of them, so we have n lines here, k lines here, and different than k, then such Banach spaces cannot be isomorphic. This is very, very interesting. So it seems that okay, I didn't add that these lines have to be non-metrizable, of course. So it seems that the non-metrizable case will have different solution than metrizable case, and the question is whether we can somehow, maybe we could generalize the Michalak's result to the full generality and show similar results. We'll see. So the tool I've used in my results, I wasn't able to fully solve the problem, but here is the way I've tried to do it. Is to use, this is basically my name for this definition, Semadeni-Pełczyński derivative. There was a paper by Candido a few years ago in which he introduced Semadeni derivative. This is a very related concept, but Semadeni derivative was using sequences, and I'm using subspaces of a certain density. So this definition basically says I take every operator in the second dual, which on a set of cardinality at most kappa from the first dual, we can, for each such a set, we can take an element of the original space such that these guys are acting the same on this subspace. So we can equivalently state that those are the operators which for CK spaces are kind of like continuous on subspaces of density kappa, let's say. And of course, this subspace of the second dual is closed and it contains X. So we can divide by X and get this. The concept for this stems from the old paper by Semadeni from the 60s. I will talk about it later. But well, first things first, this guy is an isomorphic invariant, which is very nice. And Candido showed this very nice result. Of course, he was doing this for Semadeni derivative, which is a little bit different, but just rewriting the symbols, this is basically the same. So the point is that C0 product commutes with this derivative. It will be very useful. And well, this is like why it is by Semadeni and why is Pełczyński there. So the point is that there is this paper from the 60s about Banach space non-isomorphic to its square. It's actually not only not isomorphic to its square, but not isomorphic to its every power, because this result by Semadeni is way more general. But particularly, he showed that continuous functions on the space, on the ordinal space 0 omega 1 is not isomorphic to its any finite or even infinite power. And this stems from the fact that if we calculate Semadeni or Semadeni-Pełczyński derivative, it is for this space with kappa here, this is C0 of kappa. So of course, as this is a isomorphic invariant, then such spaces for different kappas cannot be isomorphic because they would have a different number here. And on the end of the paper, of this paper from the 60s, Semadeni said, well, we are considering sequences, but Pełczyński told me, maybe I should consider just sets, countable sets. But he thought that Pełczyński maybe has some ideas how to develop it, but it was in the 60s, and I don't know whether there are any results by Pełczyński about this. But I wanted to honor this mentioning of him, so that's the name, and that's the point. So what next? Next, this is another definition I developed. Let's consider this Semadeni-Pełczyński dimension, which we define by iterating the derivative. So what? The first iteration of derivative is just derivative, right? The n+1 iteration is just applied it n time and apply it again. That's easy. And what? If we define a dimension -1, it goes for the empty space. In this case, empty space is just a space of 0. And this middle condition is crucial. Dimension is equal to n if n+1 derivative is 0, but nth derivative isn't 0. Right? So we have dimension 1 if we are not an empty space. By empty space, we mean just a trivial linear space. But if we iterate one time, then we are trivial. So this is kind of the same, but iterating n time. And of course, we can have infinite dimension. There was some idea to introduce maybe ordinal dimensions here, but it is idea for later. So yeah, maybe. Okay, and there is this fact that if we embed one Banach space into the other, or this other space surjects into our fixed Banach space, then the Semadeni-Pełczyński dimension behave nicely because of it. This stems basically from the fact that this is isomorphic invariant, so if we calculate everything and just write down the symbols, this is nothing serious, but it will be very useful for the later results. Okay, and I think this is the last slides with any non-trivial notions. So we take a compact line and some cardinal. So we have a compact line, and we want to define points that are kappa inaccessible. So these are points of character at least kappa. So the point is that we have some point. We say it's inaccessible from the left if we cannot access it using a set of cardinality at most kappa, then it's like this set will have to stabilize at some point. This goes from those, well, all this theory is kind of a generalization of those ordinal intervals. So we should always think that, for example, k is equal to 0 omega 1. Then, of course, we cannot reach it using a countable set, right? It will always have to stabilize before the omega 1. So the point omega 1 in this space is omega inaccessible from the left. And we denote those two sets, right? Points inaccessible from the left, from the right, and so on. And now there is another compact line. So if we take our basic compact line, and we say that some points are inaccessible from the left, some points are inaccessible from the right, some points might be inaccessible from both sides, we kind of split the line in those points. So here it's from the left, so we add a point here, new point. Here from the right, so we add a new point here. And here from both sides, so we add 2 points, one from the left, one from the right. That's basically how this construction looks like. Yeah, this is nothing very complicated. It is kind of resembling those separable compact lines that Professor Maciejewski was talking about in the last presentation. Okay, so let's go to the to more interesting stuff. So what we can do with this? First thing is that in 2009, Gallego was able to have some characterization of the space of the form C of 2 to the kappa times 0 xi, for xi ordinal. He was using some sequential properties, so he kind of technically assumed some properties for this cardinal kappa. I'm not referring to it. Let's say that just consistently this is a full isomorphic characterization. And what I claim is that using this Semadeni-Pełczyński derivative, we can show some result very similar to his. That if we take a bunch of cardinals such that lambda and lambda prime are below first measurable, so consistently all of them, then we have such a result that these spaces are isomorphic only if the cardinals are the same. So this is, of course, a very much weaker result than his. Maybe it's possible to fully reprove it using this framework, but this is kind of like one of the interesting examples for which we can use this Semadeni-Pełczyński derivative. How much time do you have? Okay, nice. That's a long time. Okay, and now let's go to the main problem, which I was referring to earlier. So first thing I want to characterize is this space kappa C of k, where k is a product of compact lines. So I've said that for the space k we are doing this space capital K. This space this space is dependent on some cardinal I fixed before, right? So this is, we kind of assume that we have some fixed cardinal kappa here. And it turns out that we can describe this space of functionals from the second dual as continuous functions on the product of such completed spaces, let's say. And using this, we can describe the Semadeni-Pełczyński derivative of the whole space by some quite complicated C0 product. But let's not delve into details. The most crucial thing in this product is that this is some big product of spaces of C of k, where k is a product of n-1 compact lines of the same character. So here we have n compact lines, here we have n-1 compact lines, as we know, the Semadeni-Pełczyński derivative goes through the C0 products. So this dimension that we defined will behave very nicely for those spaces, right? Because if we apply it next time, it will go through here, and we will have n-2 and so on. And this is basically what we are able to show. First corollary, kind of interesting, that for compact lines, the character of a compact line is an isomorphic invariant of the space of the space K. I think this is not normally the case, but here, if we have two compact lines such that they are such that the spaces of the functions on them are isomorphic, then the characters have to be the same because of the result that I've just mentioned previously. Because if the characters are not the same, then this set would be empty, this product would trivialize, and that's it. And the second thing is that if we take some n compact lines of big enough character and a product of compact lines of character at most kappa, then this Semadeni-Pałczyński dimension of this greater product is just n. So it counts the amount of compact lines of the high topological character, large enough, I mean. This on some level resembles this Mardashich conjecture, but it is one step higher because it's on the level of compact lines, not on the level of spaces of continuous functions, not on the level of compact spaces. Okay, so with this, corollary is this characterization that if we have n many compact lines and k many compact lines of uncountable character, then for n greater than k, we have that what? This greater product will not embed into the smaller product, and the smaller product will not surject into this greater product, which is the same as the results proved by Michalak for separable compact lines. But okay, then we had separable compact lines. Here we have compact lines of uncountable character. And there is some space in between, right? So some Aronsheim lines and so on. And it's hard to say what happens then. So that's basically the remaining question, right? If we take some compact lines that are non-separable but of countable character, then can we make this product, the functions on this product, isomorphic to the functions on this product? And well, the question, as far as I know, is open. At least I have no idea how to approach it. So that's it. And as far as, this is the end of my talk. So thank you for your attention.